we had a pretty exciting weekend. We had the FIRA Taiwan Open Robot Competition in Kaohsiung, so my students and my team were there. And I believe on the last class, before the midterm, I said, oh, we need to work on the marathon markers. So the students worked actually very hard on this, and surprisingly to me, we were actually in a position we could have still won after the first day. So on the second day, it all came down to the marathon, and we could have actually won the whole thing, but the team that beat us, they are actually the world record holder, so they're a very strong team in the marathon. That was a tall order, but for the first 30 minutes we were actually matching them. So our walking gait was stable enough and at the same speed, so the two robots sort of just followed the path one after another. So it was very exciting.
What kind of robot were you using?
The humanoid robots. Yeah. So 400 meters with a small humanoid robot is actually, let me check just for interest's sake. Because because I'm usually busy with the organization, I usually don't have any good videos ever. There's lots of pictures of me refereeing and doing stuff, but I don't actually have any nice videos. Okay, so there are some. This is from Malaysia. Oh, 2013. Yeah, and I have some old ones. Who is this? Eurocup adult size. 2023. Oh, that's a qualification video by PKU. This is a new thing that actually finally is. This is a rock climbing wall that we built. Last year in Germany.
Rock climbing for the robots.
Yeah. Yeah, sure. I mean, for humans, they've been doing it for a while, right? Yeah, so this is the marathon in Germany last year. So there we actually had a 400-meter track, so it was, at the beginning it was very easy to follow it's a nice line. And then here, these are the markers. And they won again this year. Just this weekend they won too.
Is it also a matter of fundings maybe sometimes?
Sometimes, sure, yeah, but it's not like the Formula One, so it's not, or even bobsledding. I knew some of the bobsledders in the Olympics, and there basically if the company didn't like you for whatever reason, right? They would only give you the second bobsled. You'd have no chance of winning anything. Doesn't matter how good a runner you are. So it's not like that. TKU, they have a nicer robot than us, more powerful. So, but we're not that far behind. Like I said, we were in a striking distance up to the last event. But the most important thing, of course, is that I told the students you cannot use color calibration. It will not work, right? But that's, of course, what they implemented. So we matched TKU, actually, the pace. We were doing really well. We matched them up to the 40-meter mark. And then we had problems with the markers, so we had to take a penalty. And the first time we did, so then there's a 5-meter, you get pushed back 5 meters. But then if you take a penalty, you get pushed back 5 meters. And at that point, then the sun had come down enough so that all of a sudden the color calibration was wrong. So now we're in the middle of the competition. We're fighting for first place, and our students have to start calibrating colors, right? Which is always very time consuming. And this is the kind of thing that is also then, of course, very stressful. So it's very easy to make a mistake. Like usually the kind of interface that people implement is something where you click the mouse button and you select the pixels that you want. But then the robot is shaking, people are walking, so then you have some extra pixels. Then you need to start from scratch, basically. And yeah, it was a pretty intense couple of minutes. But I'll take this one. So yeah, we should have started working on the marathon markers earlier. Then maybe we could have beaten the TKU team. But that's okay. There'll be another competition. The big event is in Brazil this year, the World Championships. So let's have a look at the problem of the marathon markers. So this is what they look like. Left, right, down, and I can. I guess I wanted to share my screen of this. So here the markers are black and white, so obviously not much with the color information we can do. So the first idea that that I think would work better would be to apply some corner detection and then calculate the threshold, the number of corners, and then count the number of corners in the different quadrants of the image. So let's try that. So here is the Harris corner detector, some parameters, and then we show them. And then we can identify the number of pixels of a particular type in the different quadrants. So right now I just cut it into 4 quadrants. Probably I wouldn't do that if we want to put that into production. Then I would use more segments. But this one will give us the idea, at least, right? So you would use 4 by 4 or 8 by 8 cells, depending on how many pixels you have in your image, what kind of resolution you have for the camera. And then this would be our feature vector now, basically, right? So we say that the marker left is this. And I think this was just to show the sum function and the axis arguments, right? So, but obviously that's not going to be enough, right? Because we haven't actually dealt with any of the prompts. Like this is like I get a full image of the marker, and then I generated some features out of that. So if we wanted to do that in a real environment, then of course the images are not going to be perfectly registered for us and scaled up to the size of the image. So what would you do next? And this is, by the way, how we implemented the marker detection at the moment in our system. Basically, by looking for not actually exactly corners, but actually line segments, small line segments. But if you connect the closest points together, you would actually get the line segments that we're looking at. But what will be the next step in your vision journey to a successful project or a commercial product you want to deploy? So basically, what I always call in my first law of robotics and computer vision is that you need to know your data. Whatever you think the images will look like is most likely wrong. So it's very important that you actually start with some real data. Now, the second step that is important in this kind of scenario would be there's sort of an addendum to this. let's imagine what would happen. So we want to develop this system for the robot marathon markers. And now I tell my student, and he goes out and we take various images of the markers, like they have set up there on the test track outside the classroom. And then you start developing your system, right? So you have some idea, and then you find the implementation to that. Now, as you implement your system, there will be certain decisions that you have to make constantly, right? This includes everything from what type of algorithm you need to implement, the data structures that you're going to use. My personal experience is actually, if you do start a problem like that, I would focus first always on the data structures as opposed to the actual code that you want to implement, as opposed to the actual program, because if you have a good smart set of data structures, the code is much easier to write than if you have the wrong set of data structures. So it probably pays off more to think about the way that you organize the data in the computer so that you can process it effectively, efficiently, and easily. But then you've done that. As you do your implementation, you also will have to invariably make decisions about other things like parameters that you want to set, thresholds in your computer vision pipeline, all of these kind of decisions. And I actually think it's a really good idea to, even at the beginning, separate your data into two groups. In machine learning, this would be called your training set and your validation set. And even if you do non-machine learning based approaches, I still think it's a good idea to, if you have enough data, that you split it up into two separate groups. And one of the ones is the one you look at while you develop your code. And the other one, you just know that it exists, but you don't actually use it. So in this case, you are the machine learning system, because the problem is that as you develop your code, guaranteed you will be able to find the solution for the images or the data that you are exposed to and that that you use while you're developing your code. But really, in order to see whether it actually works then or not, is actually non-trivial, right? Because you're all smart, so you find a solution to the problem with the data that you're given, but that doesn't mean that it will work in the real use cases, right? In a much wider range of use cases. Say again?
Maybe different lighting from the
all of those kind of things can make a big impact. So for machine learning, if you do machine learning, then of course you should be aware of the fact that that it's crucially important that there is no leakage. Not only do you need to separate your training data into your data into training data and validation data, but you also, or test data and then validation data. Sometimes we do it in 3 groups if you want to estimate the performance of your machine learning system. Then you have training, test, and validation. Otherwise, you just have training and test data. But even if you don't actually use a machine learning system, it's good idea to separate out your data so that you have some data set that you have never seen yourself while you develop the code, and you would like to use that in order to then see whether your code still works. But there are some, making that separation is actually not, can be quite subtle, right? As we found out in machine learning. So if you get some time series data and you take the first 30 seconds always as your test data, and then, as your training data, and the last 5 seconds as your test data, then that is actually heavily biased, because inherently you can do a lot of prediction from the previous experience to the future. So the algorithm, actually there will be information from the test data that is leaked through to the machine learning system. And so there's a lot of things that you need to worry about. So for example, if we, and So that's why robots always work in their own lab environments, right? Because all the algorithms, everything, are the design that you have is done in such a way that it matches whatever environment you have. So in the lab, for example, you usually have like about 10 students. Most of them have seen humanoid robots before. So they won't be that excited to see the robot doing a marathon, right? When we run the competition, sometimes we gave demonstrations or competitions or demonstrations. The general public, they're very excited about it. So all of a sudden, you have 50 children running around the robot. Then your algorithm will usually not work that well, right? If you hadn't considered this. So, and it's little things too, right? Like you design a data structure for representing a graph. If or line segment, if your images would be that clear, that clean, as those here, then you could just represent that as an adjacency matrix and just have the full matrix. Now you do that with some noisy images. All of a sudden, if you represent that, instead of just having the points, like 10 of them, so if you have the adjacency matrix, then you need an array of size 10 by 10, right? Because for the adjacency matrix, you basically need the square of the size. And then, yeah, sure, 100 bytes or 100 integers to manipulate those in a computer is not a problem, right? Can do that very easily in real time. But when you actually get the real images and there's noise, then instead of just getting 10 corners, you get 100. So now your adjacency matrix, if you have the full adjacency matrix, you'd be looking at 10,000 bytes that you need to manipulate. That's a whole lot more work. Plus, it's still a graph that you have, right? So most of the connections are going to be zero. So it's going to be a very sparse matrix. So you would be much better off to represent that then as a sparse matrix and only process the 10 entries that actually have connections to somewhere else.
Connections?
If I want to do line segments, like see how close is this one to this one. Like,
okay. All right.
That's just as an example.
Yeah, okay, thank you.
Direct neighbors in whatever processing I do. You basically always have two options, right? You can represent the entire matrix, which makes manipulation a lot easier. Like your code becomes a lot easier. Or like if I have any kind of graph, let's say the markers I want to represent, right? And which connections are close enough so that I can form lines, right? Then I have 1, 2, 3, 4, 5.
Okay.
So from the diagonal, I always have all zeros because from node 1 to node 1, there's no. But here 1 is connected to 2, right? But not to 3 and not to 4, but it is connected to 5. And actually, you could get away with just taking the upper
2 can go to 1 and it can go to 3, but not to 4, and it can go to 5. And 3 can go to 2, and or 2 can 0. 3 can go to 4, but not to 5. And 4 can go to 5, and that will be it, right? So, yeah, if you have like, on a computer nowadays, even if you have 100 points, it's not a big deal. You just represent the whole thing. But if you have thousands, and as you can see, even though here I only have very tight connectivity, right? Most of the entries are 0. So if your graph just looks like that, then it may be better to just have to represent it as 1, 2, 3, 4, 5. And then I just store the non-zero entries. So 1 can go to 2 and to 5, and 2 can go to 1 and 3 and 5, and 3 can go to 2 and 4, and 4 can go to 2, 3 and 5, and 5 can go to 1 and 4. Right? So which representation is better?
The second is going to.
Oh, really?
Okay, no, for the computer, the first is.
Yeah, okay. Anyway, there's really no better, right? It depends on how many points you actually have, and what kind of processing you need to do, right? If you wanted to search this thing with for shortest path connections, for example, there's a very elegant algorithm that will fire through this adjacency matrix in n steps, and it'll give you all the source to destination shortest path that you can possibly want. If you have a sparse matrix, this is a lot harder. Even, it turns then from a 3-line program, this is literally 3 lines to solve the shortest path problems, to maybe 30 lines or something.
Okay, in terms of coding, yes, okay, but visually, if a human, like
if you were to print it out to a human,
exactly,
then you would use this. But right now, I was just concerned about the processing.
Okay, yes.
And so the point is that for the processing, there's no best solution, right? It depends entirely on how sparse this matrix is. Like if you think about it from a mathematician point of view, this would be the full representation. This would be a sparse representation of the same matrix, right? So there's exactly the information that is encoded in this is exactly the same. There's nothing hidden or anything like that in one or the other. It's just that some of them are easier to process within their environment. But until you actually know your training data, you don't know which one of those will be more efficient on a computer. So you may decide that, oh, this works fine for clean images because I only get the 5 corners that I wanted, and I can easily draw the arrow from this. Right? But then in reality, you get something like that, which you can still process. But now your matrix has like several megabyte matrix all of a sudden in order to represent that. Or it could be the other way around. It could be that you have very noisy images and you could speed up your processing dramatically by running some kind of reduction algorithm or relaxation algorithm or something. My point is not that one of them is better than the other. My point is that if you have a set of images that you have in your mind because these are the ones you use during development, you're never even going to consider what the other options are and under what condition the other option actually may be better or would be better or may be more suitable. Now, of course, if the real world then turns out to exactly match your development data, then everything is fine, but usually it's not, right? Usually it doesn't do that. So now how would we, in this particular case, how would we get training data? Well, one thing, of course, is to run the robot and generate, capture video or images. And that's clearly necessary. You do need to do that. That's an important step. I think yeah, I mean, in computer vision right now, yeah, so your project was object detection, right? In specific social encounters, let's call it this way. What idea or how do you want to approach that problem? What do you think you're going to use in order to find a solution?
My natural reaction is to do the typical train a lot of images and then detect. That's it.
Yeah.
I was hoping for a shorter way, like instead of the traditional feed it with 3 million images. Is there a shorter way for that?
Well, taking the images is maybe actually a pretty pleasurable part of your job.
No. I'm very good at that.
Yeah. But yeah, I think it's a labeling of the images and
Yeah,
just the curating of the images that would be problematic.
Yeah.
So there's sort of the whole labeling and managing the images. Is one thing left. And then
Basically, that's what I can think of at the moment.
okay, but once you why do you need to label them?
In order to find the objects that are related to that social encounter
Yeah.
in scenes.
Right, but then you assume, I assume you apply some kind of convolutional neural network
Yeah, the typical
architecture, and then you have a classifier output, right?
Yeah, that's it.
Yeah, and your job, Philo?
It's more about SLAM, but specifically I need to not only locate and map, but I'm trying to improve the pipeline, like the whole SLAM pipeline. I'm trying to improve some of the processes. So I'm
I thought you wanted to do visual SLAM.
It's visual SLAM, yes. It's Slam.
Visual Slam. Okay,
But
so let's just focus. Let's forget about the LAM part, localization and mapping.
Yeah.
We just because that's not part of the course, right? So for the visual part, then what's your approach?
It's nothing. I'm studying all the approaches that there are, and I'm trying to find what can be improved. I'm trying to find what we're doing. But anyway, in general, it's feature detection,
Okay.
matching.
Okay. Yeah, sure. So how do you get the features? Or
I'm using all right.
okay, then of course you completely break my nice narrative that I had for this particular lecture. You're doing a master's? No? Do you have any computer vision project you want to do?
No.
No? For a project, okay. Then let's have a look. Tyler, Hanjaya. So Hanjaya is working for Invintech. They do all sorts of vision. I'm not sure exactly what he's working on right now. Anyway, one thing that is the current state is that it doesn't matter what kind of project I have, right? Detecting markers, detecting object, finding features to track in the SLAM system. The modern approaches are actually also using learning to do that, right? Like Dieter Fox has he's a very good researcher from University of Washington, and he showed is he University of Washington? Yeah, I think so. He showed his 2 years ago. He showed his Vision Slam pipeline, which was actually learning the features that it was using to track. And there was a Russian team. They were doing global vision with wheeled robots in Kaohsiung. I talked to them. They were doing so their problem is like the global vision problem, where they need to detect the pulse of the robot. I don't think I have a good video for that. But they have the robot walk and they need to detect the pulse, or pulse detection for humans or something like that, right? Arm up, 30 degrees left, that sort of thing. And the problem is that basically right now with my students, and I'm not 100% sure if it's a problem, but what happens, right? What's the current state of affairs is that I can give a student any computer vision problem, right? And this pipeline will look exactly the same. And instead of just having CNN, now it will be, we use YOLO 5 as a baseline. And then we train that, we do the extra training with our images, and then we go to town. So that means that actually the computer vision solution looks exactly the same for everything nowadays, right? The only difference then is the additional training data that you submit into the system, and how good, basically then it's how good is your training data, how diligent are you when you collect the training data to make sure that it covers all possible aspects and variations, and how diligent are you and how productive are you at labeling images, right? Now, I think I mean, this is a good approach, but there's really not that much to, and it is state of the art, lots of applications nowadays. If you have a vast amount of training data, then you can actually do that, and it's going to be very high performance. I don't think you'll be able to beat that. Especially if the images are very representative of what you actually experience in the real world. I still think that the old school computer vision, looking at gradients, thinking about gradients, is worthwhile. In particular, this is also computationally a very expensive approach, right? Not just the training, even implementing it on a low-powered small Linux system would be non-trivial, right? Yeah, and I guess it'd be YOLO version 5 and Vision Transformers that people are using. And I do think that by just thinking about these other approaches, you can actually evaluate even if you decide to implement it as a neural network, you can then use that to evaluate the system. And but since this is the current state of affairs, right, where everybody wants to do that, I sort of think that maybe one step that I would do is, before I actually do all of this work with taking the images and labeling them and things like that, it actually is worthwhile to use synthetic images and generate synthetic images of the environment. And I think that has several advantages. One, you can sort of look at the best case scenario for what your images what your network is going to be able to produce and learn, right? Like, if you only show it two pixel, like clearly, if we ask the system to detect the position of the marker and the marker is like 2 by 2 pixels, then probably we won't be successful, right? It doesn't matter how many images of very tiny marker I actually produce. It won't be able to do that in practice. And another thing that the reason why I think the synthetic images are actually a good idea is that I think they may actually help the network to learn the correct features. Because one question or one problem that we have is that if I have some kind of vision task and there's these 3 pixels that are important to classify something, right? In order to map it as good features. These are the 3 pixels in that 8 by 8 pixel that are really important. We cannot just we don't know what those 3 pixels are, right? So we cannot just give them to the system, so we have to give it the whole image. But when you take real images, there is a high chance, so then all of these data I need to present to the system, right? And there's sort of a difference between human learning and neural network learning, and the way that I thought about it, because if you think about it, if you have a human teacher, right, like myself, or you teach your younger kid about what a circle is, right? Let's say you want to teach the kid what a circle is. Then, and the kid doesn't know anything about circles, doesn't know what it is. So, okay, then how would you teach it? By giving examples. So you want to do an inductive approach. You don't want to do the mathematician.
Oh, yeah.
It's the mathematician. You would just tell it, oh, it's a regular polygon where n turns towards infinity, right? That will go over well. But no. So you want to show examples. So you want to use an inductive approach. So what would you show the kid?
Drawings.
Drawings, okay. What kind of drawing?
Drawing of a pie.
Pie, okay.
A pie.
Okay. So I draw a pie.
Drawing of a donut. Food.
Okay.
Circle.
But okay, so
Or square.
so then you would show something that is circular, right? And you say this is a circle, right? And then I'm not sure what you would say for the pie. Is the pie a circle or not? Or two circles?
Two circles.
Yeah.
The inside and the
So, okay, let's take not,
Okay.
when it says, oh, that's a pie, okay, fine. Then it says, oh, pie. And then you would say,
That's not a circle.
that's not sorry, not a pie, that's not a circle, you would
Yeah,
say.
that's not a
Circle, circle, no, that's not a circle, right? But now, I think you have to realize as an educator, there's sort of two mental states that your niece or nephew could be in now, right? One would be the shape, right? I messed that up. If it knows that this is a circle, this is not a circle, right? Then the mental states it could have would be that this is a circle as well, right? The other mental state it could have would be that the other mental state it could have would be to say that this is a circle, right? Because
Closed polygon.
no. Because here, if you say this is true, right? This is a positive example. If we let's not talk about circles because
The color.
the color, right? You're not sure, is it everything orange that I'm supposed to learn? Or is it the shape that is important, right?
Okay.
Now, if so how would you deal with this as a teacher then?
More examples.
You will give more examples to understand that these are the two possible representations, right? So you may give it this one and say, yeah, this is also a circle, right? Yeah, it's a different color. And then, okay, this one is not plausible anymore, right? So then the learner can say, oh, now I think I know what the concept is. So it's actually pretty difficult, or I think as part of the teaching, what's important is that you do need to figure out from all the examples that you present, which aspects of these examples are relevant and which ones are not relevant. And in effect, that is what's crucially important about learning a particular concept. Because here we actually have three of them, right? What I showed here would be this would be the correct concept, but there's sort of another version of this that up to this point the learner wouldn't know. That will be that this is not a circle, right? Because if I say this is a circle, this is not a circle, then it could be that everything round is a circle, which is what I have here, or it's the color that's important, or really only orange round things are circles. So the danger when dealing with neural networks is that there's no way to, you can do that when you're a trainer, right? I can present and I can say, no, this is also a circle, so the color is not important. So now the system knows that it's exactly the same shape, but it's two different colors. So that means the color is not relevant. When neural networks are trying to learn that, I think it's because the way that the gradient descent works, this is actually a lot harder for them because the neural network sort of says, oh, green and or circle. If I now have negative examples of squares, it'll say, oh, a blue square is not a circle. Oh, a yellow square is not a circle. A mauve square is not a circle. A red square is not a circle. So it'll have to go through all of these possibilities before it can say, okay, probably it's a shape, right? Now, the only way that you can actually sort of speed that up, I think, is by saying, by presenting images that are exactly the same, except the feature that's crucially important. But of course, that'll never happen, because even if I take two images from exactly the same point of view, the colors are going to be, they're going to change, the brightnesses are going to, there's going to be some noise in the image. Now, there could be some spurious statistical correlation that will make the network go in the wrong direction. And using synthetic images, I think, may actually help the generalization ability of the system by being able to present it with the two different classes in what's otherwise exactly the same, right? Like if I run this through a ray tracer, I get exactly the same brightness levels. So I think when I do these kind of, when I do these kind of networks, then sort of I started to use synthetic data first to train the network to A, get an idea, B, you can bootstrap your network, right? Further training then will run a little bit faster. And to reduce the amount of training data that I actually need to label, I'm not 100% sure if it actually reduces the amount of training data, but the other advantage that you have is that you can actually, the labeling is trivial, right? You just have the computer. Like I could produce 1 billion renders of the environment and I would know exactly where the ground truth is. Right? Like I would know exactly the position of the robot and the parameters of the camera. Now, if you only train it in synthetic images, then of course it's not going to work particularly well because it may not learn the variation. And so it's sort of, it's sort of the other extreme of this, right? If you only train in synthetic images, then your network may say that, oh, yeah, sure, I understand the color now here was a red pixel and it was a square, and here I have a red pixel with a square, and this pixel was exactly the same. So if you train the network long enough, it'll understand that this pixel and also the relationship of this pixel to all the other pixels cannot have any influence on the final classification, because those two inputs are exactly the same. So it would get a very low weight on that particular input. And you could train that very easily, right? On the other hand, what could happen is that you then take real images and it'll say, yep, that's a circle. And then it'll say, no, that's not a circle. Because there's like a tiny difference between those two, right? Due to noise in your camera. And now, so in a sense, I think the real images to synthetic images, you can trade off the two different types of errors quite nicely and sort of work on those, because that the neural network is sort of really good at. If there are small variations in the pattern, it learns to ignore those. And it will be able to do that quite well. So what I want to do for the class today then is to just use Blender and set up a small environment for our marathon running robot, and then we'll take some fake images so that we can use it as training data. Have you guys used Blender before? I highly recommend it. It's I actually do think it's a very important tool for computer vision nowadays to be able to produce those.
I've heard it in the context of video game development. Is that possible?
Yeah, yeah, it's a 3D. It's like Maya or.
Ah, okay.
But the thing is, the basic things you can learn very easily, and I'm really just a beginner, but they can do amazing things with Blender. Like, it's a full it's a full 3D So if you're skilled enough, you can do this with Blender. But I can't, like, not a hope. It's really, really hard to do it like that. But you can do, what I want to bring across is you can actually set up a simple environment very quickly and then write your Python code in order to be able to generate synthetic images. So this is all animated using Blender. So for me, I guess, I mean, this looks really tough, right? I'm sure the Veka, for example, Xiao Hong, one of my former students, she works for Veka, which is the production company, Peter Jackson's production company that made Lord of the Rings and Gollum and King Kong and those things. So I'm sure they have better software. But actually, the software that they use is crazy. Like for the for Avatar, she was doing Avatar, and there, what was the name of the software? I forgot. But the software you cannot even buy it. You can only rent it for $20,000 a month, and and so the Angelina Jolie was in that movie, I think, and for the animation for her character on the computer generated 3D model, they had a rig that she had to sit in front of, and it had 9 cameras, 9 high resolution cameras looking at her face to do the facial animation. Because like, okay, I look at this, I know it's not really human, right? But they wanted to get this more and more realistic. So they had, for the motion capture, they had this huge stage with, on the order, I can't remember exactly, but on the order like 20 to 30 cameras with the infrared transmitters, and then they were wearing the motion capture suit, and then they would walk around and you can get very high accuracy motion data about how they move. But the face, then, for the face alone, they used 9 cameras. So this is also free and open source software, so you can download and run it legally. Without having to pay for it. And I don't know if I've shown you this one before, probably I did, but so you watch this, right? Blender movie. Hero's Journey movie, I'm sure. Oh, another fight. Okay, so you see this kind of animation, right? My own attempts at doing animation are a little bit more, probably not quite so good, but I did make are a little bit more pedestrian, but I did make the bear in Blender. So, I mean, almost the same, right? Like not really that much difference from here to there. Yeah.
But now the question is, like, why the bear? Like,
What? Yeah, tiger, you know.
Oh, the Taiwan bear. If you,
Taiwan bear, okay.
if you,
There's an orbit that goes on. Oh, this is so fun.
if you look at the front, there's the V shape, which is the Taiwan bear. It's a small black bear that only lives in Taiwan. See, so it has that front V in it.
okay.
And So you can see basically the graphics almost hard to say which one is done by me and which one is done by the other guys.
Clearly they're both very clear.
Well, maybe it's the music.
Makes sense. Makes sense.
Yeah, everything is better with music. Oh, now where's the bear going?
The bear's going. And then if you move, the bear will run.
No. This is just because the whole thing is so you can practice your driving, right? So, and the kinematic model and the dynamic model of the scooter is actually, hey, how come I can't steer anymore? Oh. Yeah. So now I have the scooter upright. I reduced gravity, otherwise it's too hard. But the problem is if you then just drive, it's kind of boring. So now if you get too close to the bear will attack you. And then...
Did you code this behavior or?
Yeah. The coding part is easy. For me, the coding part is easier than drawing the bear and doing the animation of the bear so it can stand up and everything.
Wow, opens a world of possibility.
And this is then the blend I imported. I wrote, I'm not sure if I got or I imported the importer. Then from Blender I can put it into Three.js and then it just runs on any web browser.
If you gave your driving character health points and the bear an attack point 20 years ago, this would have been a finished game.
Yeah.
This would have been a target.
Actually, I don't know if you guys know, but maybe I shouldn't. So if you know about this is actually the abandoned DOS games from the 1990s. And I started playing those again because I just started playing Space Quest. So then these are actually really fun games, right? And they, what I realized is that I don't play that many games, maybe once per week I play an hour or something, but or an hour throughout the week with when I have time. But what you realize is the games nowadays are, and I don't play any AAA games, so I don't know about like what was currently popular. But I like the Final Fantasy. Final Fantasy I like, and the Fire Emblem. Fire Emblem I like because it's kind of it's kind of like a fantasy chess thing that you play in. But anyway, what I realized is that the games are so much harder in the 1990s than they are nowadays. It's like no comparison. I only started playing the Space Quest 2 weeks ago, and it is incredible. Like nowadays, what was the last adventure game that I played? It's kind of like the RPG games, like Final Fantasy. When you play those, you don't really get stuck. Like I don't remember ever in the last 10 years ever having to save a game. Like it would all be autosave and you just keep going, and you never get stuck. Like there's never any point where, oh, you didn't pick up the scepter of Zeus and now you don't have it and there's no way to go back and pick it up, right? So you didn't have to save. So this thing now, it's brutal. Like you walk off the cliff here, boom, you die. Oh, there's a hole. this is kind of like an adventure game. You have to click on thing. Actually, you can play them in the browser too if you want to. So you say, oh, look, oh, there's a hole. Look into hole. Oh, the big beast ate you. Boom, you're dead. Or you're in the spaceship. Go fly to these coordinates. Asteroids showered killed you. Boom, you're dead. And if you didn't save beforehand, then you have to redo the whole sequence again, right? So they killed you off in those games way earlier, way more than they would do nowadays. But these are kind of funny games. But this is not actually the one. This is the one I'm playing. Spacecast is also good, but no, not. No pictures. Yeah.
This one.
This is Return to Monkey Island. Oh, this is the other one is The Secret of Monkey Island. This is the new version. I'm playing the one from 1990, which is very funny. Like it's a fun game. Yeah, that's what it looks like.
Sometimes I wonder how they did some of the stuff we did back in the 90s and the 80s. But then
Oh yeah, the programming was.
this article and he said like video games industry actually they pushed a lot of the development.
Oh, for sure, yeah. People wouldn't buy graphics cards until they had to play some of the 3D games, right? But then they became huge. So Nvidia basically. But what I like about the Monkey Island game, what I think is really clever and really very creative is here. I'm Guybrush Threepwood. That's the guy's name. And for that game, you have to fight the other swords guys. You have to do sword fighting with them. But when the way you do the sword fighting in the game is you have to go to the teacher and then it's all based on the taunting. So the guy will say, oh, you are as weak as a little turnip, and then you have to answer with the right response. They say, oh sure, but a turnip can still hit your head, and so that you don't actually do any fighting. The only thing, they never actually cross blades. They only taunt each other until, and if you have the right response for all of their taunts, then they just give up and say, okay, no, you're the better sword fighter. So I thought that was really clever. That was kind of fun. But now let's get back to Blender. Got that guy. And okay. So it's a 3D drawing program, and we'll start even simpler than the Taiwan bear. We can just start with a cube. Then you can go to view and have a look at the point of view of the cube, so you can rotate it to the top and look at the front
Here are your axes. Red is the x-axis, blue is the z-axis, and green is your y-axis. And there's tons of Blender tutorials. I don't want to go through this right now, but let's make a domain for the marathon run. Now, in that case, I'll just take this cube and I can hit S to scale it and then scale it in the z-axis to 0.1 and scale the z, the x and y axis to 10. So then we have kind of a playing field. Right? And I have a camera that I can select and then can take the view from the camera. And then here's what my camera sees at the moment. So now I can give this color, material, so hope that's the right one. Maybe set it to this. And then I can render. And you can add lights too, so I can add another light. And then G to grab, and then you can move it around. And let's move the camera back a little bit. And then R to rotate. So here I can sway R. Or maybe I bring it to here and align it. And then I can set up a simple environment with adding some cubes. And I just have to make sure they don't float in the air. And add a new color. Let's make one red cube and a blue cube. And here, because the scene is so simple, I can actually render it directly in the viewer. So now, how much power? 10 watts? 1,000 watts. That's why this one doesn't do much. So I can set the power of the light. And let me have a look at it from the top. Grab this along, no. I'll grab the camera along Y. And then with N you can get the parameters, so it shows you the orientation in this case. So I think I want to change that to Y. And the location, so X, Y is 0, 5 meters high. Oh, and the other thing you can do with Blender very nicely, which is what I've done before, is you can also use it to make models for your 3D printer. It's quite capable of doing that as well. So now I wanted to add the markers. But, I mean, there is plane, right? But I always get confused with planes. I don't really know whether the mapping, the texture mapping actually works correctly. So I usually just always use a cube and scale Z, so SZ to something very, very small. And then that's also like a and I can make that black maybe. See, now I have that, and I actually want to bring it all the way down to black. And then I need to download my images. Oh. Okay, save the image. And now I can save it. Yeah, okay. Oh. And this was marker straight. So here we want to apply a texture. See if I get that correctly. Image. Okay, the texture is loaded, so texture paint. Now it doesn't. There's something I've forgot. There's two modes, object mode and vertex mode, which are important to keep in mind. And then, let me see, my texture is not aligned correctly. So if you just want to move a single, maybe a single vertex, then you can do that. Other than that, I think I have to take those two. No, it doesn't. Let's try that again. Front, add, cube. Ah. Okay, view the top, scale 5, and then add a texture. No. Marker 3. size now. And then pre-crop sampling. Okay. I don't have UV unwrapping mode there. Ah, that's why you showed that. So I would have to map. I would have to map that to the bigger part, I guess. Hmm? Let me get this one G. No. Unwrap. That's that face. Okay. I can only employees landscape. Oh, okay. Oh, now I can move just one. Oh, weird. Then let's see. Okay, now we have a marker. That I want to bring into the world. And then I can duplicate this and push it around anywhere I want. And I can also add the other one. So then I can go to the camera and render some views. Okay, let's rotate those. So at least, yeah, of course I can rotate it in any direction. So rotate Z, rotate Z. Yeah, come, I cannot rotate this now. Oh, it's in Chinese mode. That's why. So that's why I didn't understand any commands. Right. Here we have that, and when I look at my viewpoint from the camera, okay, rotate that 90, that 45, that minus 45. Grab this one in the Y direction a little bit. Grab this one and move it to here. Rotate. And so then this would be our environment. I can also, I think that's okay with the camera view. So then we can render an image. Which would give you pretty good test data. Now, the other thing that is important for that or for this kind of workflow is that you also have a Blender console that allows you to do scripting. And that one is actually very powerful. So here we have the scene, and then you can select. You have it's all done in Python, and things take a little bit used to, but take a little bit to get used to. But after a while, it kind of makes sense. So in our case, for this particular image or for our particular application, what I really want would be one neat trick is as you edit in the interface, it actually shows you what the internal command is that the 3D rendering engine applies to the data, and then that means it's actually, if you have a complex workflow, you can actually do it with the hand first, and then just copy and paste the commands into the Python shell. So here we have a new one, and then D, and then you can do discovery. So D shows you what kind of things are available in the world, which is a lot of stuff. Most of the ones I don't know, but or what they actually do. But the materials and the objects would be the most important ones. So here it shows you all the objects that we have, and then I can have a look and see what data is available for the first cube, for example. And then I'm not sure if print will do it. Let's just that one. Okay. And then here's all the values that are available. So in this case, if I wanted to find the markers, then what I could do would be I can look at the scale of the objects. That should print it out. So that tells me that it's a vector 0.5, 0.5, 0.5. So that's not one of my markers, because I scaled them all to be 0.001, right? So that would be one way. Of course, you could also, if you were to do that, this would be just a hack. You could have just called them markers. This is actually a cube, and then this one is another cube. So where is this cube then? Oh, that's the playing field. And then this is a cube, so we'll call that obstacle. And then this one is a cube, we'll call that obstacle. And if there's already one, then it'll make obstacle.001. And then this will be marker. Marker And then here I can now check. So these are the markers that I have available. And here's the position. Pose. Location it's called. And rotation. Different ways to represent the rotation. Let's go for Euler angles. Or I can also ask for a quaternion. Now, in this case, it doesn't really matters. And what's 3 then? Rotation angle. It's a 4-entry vector, so strange. I think that must be the quaternion. And so that means here I can get the position. Of our marker. Oh no, sorry, that's rotation. Here I can get the position. And here I can get the angle. So that means I can just read out the ground truth for the objects. Was the ones that it said? Yeah. Yeah, you have to start it from the shell, like from the command window, to see the output of print. So how were you supposed to do that? You can generate a file. Or in JSON format if you wanted to. And let's see. right line or right? I did an error. No such file or directory. So what do we have on this machine? D. Oh, no Jackie, okay. And let's save that in D too. And D and oh, I already saved them. What? Okay. And what was that then? Blender marathon markers. Blend obstacle run. Oh, obstacle run pictures. No, nothing with marathon. But I can use the same thing. So here now I get the output of the object. So I can say if o.name.start with marker print o.name starts with okay. Hmm. Hmm. Ah, it's not print, it's a write line, of course. Depth location 0. Location 1. And O dot rotation. Rotation Euler 2. almost, yeah. And now here I get the different objects with their names, so I can call them straight and left, and it shows me the XY location and the rotation around the Z angle in radians. Like this one here is 90 degrees, pi over 2. Then you can just use that as ground truth. Instead of having to label, you can just tell it where the position is, right? And of course you can produce a million images that way. So I think that's kind of good. So now I just want to add the other markers. Modeling. So I shall I just duplicate this one. That'll probably be the easiest. Duplicate this one and then change the texture. Let's see if that works. New image, no, open image. Oh, I only have the straight marker so far. So let me get the other one. Save. So this would be marker right. And while we're at it, we'll also do marker left. No, not all of them, just one of them. So let's go back. So that means I need to have a new material here. No, 5 here. So that means I want to add another one. Image texture. Outer right. So this one is material marker straight. And this will be marker right then, hopefully. So here we have this base color. And here. So here I want to remove this one. Oh! Okay, now I think I made a copy. Oh! How come two switched? Oh, because I selected both of them, of course. Eh? Ah, they. Yeah, when I duplicated them, I parented them, so the material is going to be the same. So I have to undo the parent thing. Object, clear parent. And then, okay. So then we go plus. Marker right, okay. And then, yeah, okay, so that works now. Now I can switch individual ones. And here I can make a marker left. So that means texture one. I don't actually need that one, I guess. Yeah, marker, new material. M marker right, so now I need M marker left. And that will be removed. And here we want the texture, image texture. Open it, mark, what did I say, left? So there's a right marker, left marker, straight markers. I can save it, and this is what the world would look like then. Now the other cool thing you can do for sort of video or computer vision is you can actually animate the camera and make the camera move and have the camera rotate around things so that you don't just get a static scene, but you actually get a video of what the fly through would look like. Now looking at this, I think those are actually a little bit too big, the markers. So if I select all of them and say I want not the Z coordinate affected and half the size, so 0.5. And I was sure I could. I think that'll look a lot more like our images. Yep. And then leave it at that for now. So until next class, you should try and play around with Blender a little bit, generate your own environment. Now, if you want to do something else, instead of the marathon markers, if you want to detect some other objects like features for SLAM, or in your case, I leave it up to your good judgment. Maybe we're looking for lollipops instead of your actual target. Yeah.
That's easy, that's very
Yeah. And you too, you should try and generate a Blender environment that allows you, and then also have a look at the script. I will actually upload the file just to get you started, but the scripting part is really powerful. But of course you can also use that to generate images and objects and things like that. Right now I just used it to extract the information that we need. So I can extract the position in the real world coordinates as well as the pixel coordinates of where they are in the image. So then we can check bounding boxes and things like that. And so where did it save? In D somewhere. So these can be enormously big, of course. But simple scenes are also quite simple. 1 megabyte. Now another thing, just as a side note, another thing that happens
happened at the robot competition, which was quite an important learning experience for my students, was that our archery team, they actually worked quite hard and they did a good job. So when we did the testing, they were hitting like 3 into the red, which is a good performance. And then when the competition started, they missed with the first arrow, which because the target is moving, right? So it's going on a circular track, so it's not just a static target. So the timing was just a little bit off, and we missed the target. And then the second one, they were actually probably they were in a good position to score because in practice it worked quite well. Then the girl brought out the robot, put it down, and has the keyboard and hits play, enter, right, to start. But it didn't work for whatever reason. And the problem was nothing to do with the robot, it's just that the enter key didn't come from the keyboard to the robot. And then, now they had missed 2, so then they were already extremely nervous and agitated, so then the other ones didn't go so well either, because they sort of lost confidence and put themselves under a lot of stress. But the important lesson there for real systems is that our robots have buttons on them, right? And by introducing the keyboard to the laptop, so the wireless keyboard to the laptop via the Wi-Fi to the robot, you basically introduce 2 additional points of failure that didn't exist before, right? Like, it could be, I have no idea what actually happened, but it could be that the keyboard just didn't have any battery power left at that point, right? Which would tank all the hard work that you didn't matter anymore if you cannot start your robot, right? And it could be the Wi-Fi connection to the robot, right? And by not using the button on the robot, introducing 2 extra points of failure is always a dumb idea for any system.
Point of failure.
And-
It's the first time I hear this.
Pardon?
Point of failure. It's the first time I hear this concept. But okay, it's like any part that can
break.
break. Okay.
Yeah. If you have a button that's connected directly to your processor,
Yeah.
to your single board computer, I mean, yeah, that's one point of failure. The button may fail, the cable may break, right? But that's a whole lot more direct than network layer to Wi-Fi, through access point to your laptop. I mean, that's a whole other change there that can make your system fail. So by and then they said, yeah, but the button sometimes doesn't work either. But then the point is that we have tons of other ways to start our robot, right? We could have programmed, I could leave the head servo powered off and simply check the position of the head servo. If I move the camera forward, then the robot starts, right? Again, that is directly on the servo joint to the computer. There's no Wi-Fi, no network involved. Right? I could have used the IMU. I can just shake the robot and say 3 seconds from now you need to start working. Right? That would work as well. And so I couldn't hold up 2 fingers in front of the robot saying now do archery. And if I hold up 3 fingers, then do something else. And I could have combined all of these. But the one method that they chose introduced, that just didn't work that one time. And of course things break, but you have to think carefully about the points of failure in your system too. And this is exactly why I do like the robot competitions, because when you do assignments as an undergraduate student, you never have to worry about these things, right? Because like your assignment, okay, then it doesn't work, you just restart it, and you can run it again and generate the output. But if you have to run it at this, at like 9 o'clock, the referee blows the whistle, your robot better be working. So it's a very different mindset that you need in order to be successful in this.
To be more robust, more fault tolerant.
Yeah. The three, that's also a common saying, not mine, but I forgot who came up with it. But they usually say the three most important things about robotics is robustness, robustness, and robustness. So, but I think it's very apparent in robotics, but if you develop code for Google, it's actually the same, right? If you bring down Google search, that would be huge, right? And even for smaller companies, like if you do, what kind of programming would you be likely to do? Like I mean, if you're a business, if you develop business software and the payroll doesn't work for your 5-people company, you have five people that can't be paid, that's huge too, right? And if you say, oh, it's only because Microsoft updated the version of the JPEG decompression library, so when I want to show the logo, it didn't work, and that's why nobody got paid, then that's still horrible. So I do like the mindset that you need to get into when you're developing these robot systems. Because with some of my colleagues, we always, there's sort of discussion amongst the professors, often about how good the students need to be, not at the master's level, but how good do the students, how good of a developer should they be before they can graduate with a bachelor degree, right? And then my colleagues, they were saying, oh yeah, well, they should at least understand recursion, right? Because they're the traditional computer scientists. They were quite a bit older than me, and for them, recursion was like the beauty of computing, and that's what it was all about, right? And others are like, oh well, they have to at least have had a C course, and at least they have to be able to do some assembly language programming, and so the kind of levels that they work on, right? The minimum skill set that they need. And I said, oh, I don't care about any of that. I always think my students are going to be writing the control software for the nuclear power plant next door. And then they're all like, oh my God, no. I'll just see mushroom clouds everywhere now.
Actually, I feel that the standard that was expected of me during the bachelor and the master's here is a bit different, because while I was doing the bachelor, I did pure computer science. So it was, they had higher standard, not higher standard, but they had high expectations. Here, I've done modern networking, I've done, what else? I've done advanced database, now I'm doing reinforcement learning. And I think it's because there is a lot of domain knowledge that I need to include into the code. So sometimes I feel like, okay, as long as it works, the important is that I absorb the new concepts and the new, I don't know, because before what I did was more just programming, just coding for coding's sake. Instead now, it's more like real, or also robotic vision, no, it's more real world application. So it's more like there is something else going on other than the code, like your purpose. So for now, it's just fine as long as it works.
Oh,
So there's not that much testing and formatting.
yeah. Just let me know before you start developing software for the new
Okay.
Airbus or anything like that. Let me know. Like I had one student, and she she wanted to do a master's, then she wanted to switch to a PhD, and things were not going well. Now that of course could have been my problem, but the final breaking point was when there was no progress on this particular project, and then I asked why, and then she told me that I have to buy a license for Microsoft Office, and I'm like, why? Like can't you use LibreOffice or something? And why do we even need to write? What do we need Microsoft Office for? And she says, oh, because the installation instructions for the Java 2EE Tomcat server were in a .doc file, so she couldn't read the instructions on how to install it, right? But
That's shocking.
she also told me that she had been writing software for a bank, and I'm like, I need to know which bank if I have money there. I don't know what you call it, because this is like I felt. I mean, I think I would argue about the standards that I expect from my students. I certainly believe that they're reasonable, right? And you may be able to argue that they're a little bit too hard, a little bit too easy, right? But I cannot install the software because it's in a .doc file. It's
Wow.
way out. Like this is several standard deviations beyond what I'm willing to
Off the
accept.
top
Right?
of my head, go to an online converter, install open software.
Yeah.
Oh my god. What you have what background was she from? What did she study? It's impossible she studied computer science.
No, she studied computer science and then started working for a bank, but not in the
That's it.
country.
Maybe it's working in a bank that makes you very. You can't think out of the box. As soon as you go corporate, like you become.
I guess so. But the thing is, so.
Wow.
And then she moved to Canada. So. But it wasn't a problem with her English. Her English was good. But so then I said no. I'm sorry, but I cannot.
Yeah. She was already in her PhD, or this was master's.
She had finished her bachelor and she wanted to do a master's, so she became my master's student.
Okay.
And then I had set some projects for her, and one of them was with the Canadian. What were we doing? It was a database, health database for Inuit people in Canada. And so the idea was that the tribes could organize and sort of keep a record of their of the average health of the tribe and special cases, and they could upload it. And when
Tribes
you do,
in Canada.
yeah,
Okay.
yeah, in Canada, and but I can't say which country she's from without encouraging stereotypes. So I don't want to say anything about it. But
I
that
really
was
don't think the country that I can think of easily so many people that would be like. So I don't think it's.
Yeah. So I think it's more individual concern.
is a problem for science. I mean, there's lots of papers and it's changing now dramatically because of all the resources that are available. But like 20 years ago even, if you produced some results about your planning system, nobody would be able to run the code that you wrote to do this. Right? A lot of the machine learning papers just had the theoretical results and that was it. But now it's already a lot better, right? Because a lot of the papers with code are with GitHub repositories where you can run Llama 2 and Llama 3 now that just came out and all of those things. So it's actually a lot more reproducible, which means that the results are a lot more meaningful for science. Right? So I think that's a hugely positive effect. But there are some complaints and some concerns that some of the software that was developed is not actually very good from a computer science perspective. Like it's not very portable, it's not very manageable, but that is getting to be a problem less and less, I think. Certainly from the companies like Google and Facebook, they have excellent developers, of course.
They also
in this
follow
area.
OSCE, not just the standard regulator. There is an entity that established things like standards for codes, or like no personal computers at work, no personal.
NIST or NIST will be the one in the US that
No, this is more like an international standard. But anyway, like the big ones, yes, but like smaller ones, like we had 1 year ago, we had the local transport company in my region, Campania, and basically they got hacked, and they were saving passwords in Clear. They were encrypted in Clear. The files circulated, email, password, and that was thousands of people, including me. So that's shocking because anyone who's even touched security, even just
would know not to store
the first thing,
passwords.
you don't store passwords in Clear. How's that possible that 1 year ago there were people, developers paid by the state, and they were saying? So sometimes I think it's also because, like, if the engineer makes a breach fault, he goes in jail, he gets the process, etc. But we still don't have a lot of maybe law enforcement for these kind of responsibilities, and that's why we're still like, okay, we just copy, save, I don't know. We don't perceive the damage we do when our systems are not robust.
I think there has been a long time there have been calls for people to be able to have a professional accreditation. Like the way it works is that actually the universities, they do their exams and everything, but if you graduate with an electrical engineering degree, right, you still need to be accredited by the professional accreditation. I think given the impact, the potential impact of the harm that we can do with computers nowadays, I think it's extremely important that we have a professional accreditation for software developers. And I don't think that means that you're not allowed to write code until you went to university. I don't think we mean that, right? But if you write code for Airbus, you better have some kind of credentials, right? It's not like, and this guy, he wanted like $50 an hour to do his development, but I talked to my friend Joe, he just left high school, he can do the same job because he's very good with Excel. He's been doing Excel macros for me like you wouldn't believe, right? So he can do that code for the autopilot inlay. So I don't think we want to live in a world like that. But there's been always
computers have developed very fast, software has developed very fast because it was very easy to enter, right? If you want to become a bridge builder, it's a lot harder. They don't just let you build a bridge.
Exactly, that's the point. That's the point.
But which is a good thing in a sense, right? But it also means that there's potentially 1 million of bridge builders that would be really good that never had a chance because they couldn't get over the first hurdle. But given the amount of harm that we can do with, and I think there could probably, I think there should be different levels of software development experience required for different kinds of jobs. If you want to develop the next Fluffy Bird for Android, sure, fine, go ahead. You don't need to have a security clearance or a professional programming clearance for level 3, right? But if you want to develop software that's on the internet, I think at a minimum you would have to have security, like having been taught the necessary security issues that are relevant to internet. Because like things like storing passwords in the clear has been shown to be bad practice for the last 30 years. No, not 30, 20 years. For 20 years, you knew that you should not store the password. You should only deal with the hashes.
Oh, it's not going to happen to me. It's not going to happen to me.
Yeah, sure. But I have to admit that, I used to be the president of FIRA for the robot competition. Our website, I never actually registered because I was always the president, so I just told them like I need this and this, right? So then I registered, and they sent me my password in clear text too via email. Now they didn't actually store it on the server, but still they send an email with the password. And then I had nothing to do with the development of the web server. It was done by a company in Iran with through our Iranian chapter, like the Iranian group. They said they can develop the website, and then they hired the company. And then of course I told them, what the hell are you guys doing? You cannot store the password. Oh well, we don't store the password, we just send the email. Don't put it in the email even, like the password.
Sometimes they do is like, oh, this is your password, please change it at the first login.
Oh sure, yeah.
That's one way.
I don't remember now exactly. But there is certainly a lot of good practices. But I think that's also why, like, I'm kind of a hands-on guy when it comes to computing. But there's no way I would want to run my own mail server now or my own web server, or like CMS. You would have to basically watch like a hawk for all the security issues. Even if your website is used by like 10 people in the world, right? That doesn't matter because it will be scanned. Like I did tests in about early 2000 on the internet. If you pick a brand new Linux machine, and at that time there weren't so many firewalls, and they weren't so good. But at that point, when you put a new server on the internet, you would have SSH login attempts with standard passwords like CVS, root admin, or root god, or all of those. You would have them within 30 seconds. Like, it's just unbelievable how, and nowadays probably less than 10 seconds, right? They will try and break into your system. And if you have any of the known vulnerabilities, then of course they will backdoor you. They will then use that as a jumping off point or a proxy or relay for other attacks. gets you into trouble. But if you have paid attention, the most exciting thing about security was the XZ compression library attack, supply chain attack on the Linux kernel. That was that happened last week, and it is just unbelievable story. Like, and I'm sure it was either the Chinese government or the Russian government, and because this took like 3 years, so this is a lot of dedication to try and break into the system. So you should read about the XZ compression library attack. It's like a James Bond story, kind of, a little bit. Less shooting, but a lot of social engineering. Anyway, that's it for today then.